Good day, my name is Dullien. I'm CEO of a company called Optimize, and this talk is titled, Where Did All These Cycles Go? A little bit about myself. Before starting with performance work, I spent 20 plus years in low-level security tools and research, and worked on things like patch diffing, binary code search, malware analysis, and at a bunch of low-level security issues surrounding hardware failures like Rowhammer, and on the analysis of low-level allocators. I came to performance work because security work is always fundamentally about human conflict. And in performance, the skill set is very similar, but your results actually make things run faster, better, cheaper, and in the end, more energy efficient, which means CO2 reduction. And I found that to be very motivating. I'm known as @halverflake on Twitter. And well, when I do have some free time, I like to be in a hammock. Realistically, that doesn't happen very often these days. So the talk is titled, Where Have All the Cycles Gone? And it presents interesting places where CPU cycles are lost or wasted in real-world production systems. The insights from this talk are all obtained using real-world systems where we deployed fleet-wide and system-wide continuous profiling, and then we gathered the data and analyzed it, and this talk just presents the different places that we found where, surprisingly, cycles were being wasted. So these are all real-world case studies with some surprising results. The results of these analyses can be grouped into a few buckets. One bucket is misconfiguration of the underlying operating system that interacts poorly with assumptions that the software makes. Then there's surprising behavior of dependencies, where some software you're using does something that you didn't expect. There's suboptimal choice of dependencies, where you're not using quite the right version of the software that you should be using, or quite the right variant of the software you should be using. And then one repeated issue is paying too much for serialization and deserialization of data versus computing on the data. So let's get started. The classic issue that we see time and time again, although decreasingly so, are clock sources on AWS Xen instances. So the background there is, let's say you've got a big distributed database running somewhere, like a Scala cluster or a Cassandra cluster, and then you try to figure out, where are my CPU cycles going? And what you see is that you're spending 15% or so of your CPU inside the kernel trying to get the current time. That seems like a very weird thing. Like, why would you be spending so much time of your CPU in the kernel trying to get the local time? In order to understand this, we have to look at something called the VDSO fast path within Linux. And what happens there is that the user space application wants to call gettimeofday, and gettimeofday should be a cheap system call because people want to use it a lot. So within the libc will then forward that call to get the gettimeofday call to something called the VDSO. The VDSO is essentially there to check, do I really have to do a user space kernel space transition? Or can I get away with the VDSO fast path, which allows me to just return a value that I've derived in user space somehow? If that is possible, then do this. If it's not possible, call to the kernel, get the real data, and continue. Now, the VDSO fast path makes gettimeofday very, very cheap on modern Linux systems. Unfortunately, though, on old AWS instances, they're all based on Xen by default, and they're configured to use the Xen time source. And these AWS instances, therefore, disable the VDSO fast path by default. So that means that many databases or other pieces of software that assume that gettimeofday was extremely cheap will out of a sudden incur many user space kernel space transitions that they didn't anticipate. So you maybe have something like Scala or Cassandra doing hundreds of thousands of gettimeofday calls a second, all assuming that this would be super cheap to do, but now incurring a full context switch in the process. Interestingly, it's really, really easy to configure a different time source, like the TSC time source for gettimeofday. And it's essentially a two-liner in the shell. And there's more details at these links. But most people don't realize that this is happening in the first place. Now, luckily, the entire thing is increasingly less an issue because people are migrating to Nitro instances. So modern instances like M5, M6i, and so forth are no longer Xen-based, and therefore the entire issue goes away. But what's important to recall is i3 instances, which are the instances that have fast local SSDs, are still Xen based. And that means that if you're running your distributed database on a group of i3 instances and you haven't changed the clock source, then most likely you're wasting a whole bunch of CPU cycles just getting the time of the day all the time. The second interesting finding is Kubelet surprisingly walking directories when you didn't anticipate that it would happen. Now, it's a similar murder mystery of sorts. You start getting your profiling data and you see a sudden and mysterious jump in CPU consumption originating from Kubelet itself. So in this diagram here, we've got different containers eating CPU cycles. And then we see a sudden jump where Kubelet is starting to consume a non-trivial amount of compute. And why is that? Why would Kubelet, that's supposed to be a very thin layer just orchestrating the other containers, why would Kubelet itself start eating so much CPU? So when we got the data from the machines, we then created a flame graph and examined the flame graph. And what we see here on the left-hand side is essentially all Kubelet. So let's zoom in a little bit. And as we zoom in here, we see that we're spending a whole bunch of CPU time in this file path walk. So something is walking the directory hierarchy and spending a lot of time in it. So as we go up the stack frame, we get to something called fs get your usage and cadvisor. And as we go upwards further, we're somewhere in track usage. So somehow cadvisor, which is part of Kubelet, is spending a lot of time walking directories. Digging into the source code a little bit more, it turns out that the underlying issue is that cadvisor tracks disk usage of your ephemeral layer of every container by doing recursive directory walks. So every minute, cadvisor will walk the ephemeral layer of every container that's running recursively in order to calculate how much disk space that container is using and whether you're still within quota, and in order to report statistics. So what this means is that people deploy containers and they make use of the ephemeral layer of the local file system, assuming that this doesn't have any negative side effects on the rest of the system. But it turns out if you create very large file system hierarchies or just many files on the ephemeral layer, you will start you'll start causing a lot of work for Kubelet because it has to walk these directories all the time. And you can even end up exhausting your IOPS on an EBS volume by doing this. So this is all clearly not ideal, and also a bit of a surprise because nobody expects Kubelet, of all places, to do all these recursive directory walks. Another interesting thing that we found at one point was spending a lot of CPU time throwing and catching exceptions. And this falls into the category of not using quite the right version of a dependency. So the symptom here was we had a large Kubernetes cluster in which the user was running a machine learning workload that was mostly Python based, but the Python code would call into XGBoost version 0.81, doing some linear regression on the incoming data. None of these instances had GPUs installed. And when we started profiling, it turned out the most heavy function on that entire cluster was a function called determineInfo inside the libc. And this determineInfo function is used to map an address in a code section of an executable back to a name. Now, why on earth would a machine learning workload that spend all its time trying to map addresses in memory back to symbols? So we followed the stack trace further, and what we found out that the determineInfo function was called from a deep learning library and the DMLC stack trace function itself. So DMLC is a deep learning library or distributed machine learning library, and that library was trying to create a stack trace itself. And our stack trace essentially shows the code that creates the stack trace. And if you go up the stack trace that we're looking at here, there's a throw on CUDA error function. So we see that a CUDA error is being thrown. Why would we be throwing CUDA errors on machines that are entirely CPU based? That is also very strange. Further investigation revealed that XGBoost on any version lower than 1.0 will always try to talk to the GPU first. If no GPU is found, an exception is thrown, caught, and only after that is done, the code falls back to using the CPU. And determineInfo was called during the creation of the backtrace that would be logged on throwing that exception. So the solution to all of this was you recompile XGBoost with CUDA support, without CUDA support, or you upgrade XGBoost to a new version, and you got a whole bunch of CPU cycles back for free because your library wasn't quite doing what you anticipated it to be doing. The next section is about zlib versus zlib-ng, and this falls into the bucket of not using the right dependency when you could be using a faster one. Now, most deployments out there spend the majority of their computing time not in the code that the user's writing themselves, but mostly in dependencies. So in any given large deployment, the code written by the owner of that deployment is likely in the minority of CPU consumption because everybody uses a lot of open source components these days. And careful choice of these dependencies can make a pretty huge difference. Interestingly, in larger infrastructures, compression is often a surprisingly heavy component of any workload. When Google started doing fleet-wide profiling, they found out they were spending 10 to 15% of their fleet in zlib, and that's caused a whole bunch of compression-related research there after 2010. Now, we often see sizable clusters of 2,000 cores and more spend 10 to 20% of all cycles inside zlib. And then when you see such a heavy use of compression in your cluster, the question becomes, how can we get this to be better? And there's usually two choices. There's the choice of choosing a better compression algorithm than gzip, and then there's the choice of just taking a faster drop-in replacement. When it comes to choosing a better algorithm, it's important to realize that compression libraries can be compared against each other. And there is something called a Pareto frontier, which essentially says, at the same amount of speed, am I getting the best possible compression ratio? Or at a given compression ratio, am I getting the best possible speed? And ZSTD is a compression library that Facebook is developing that explicitly aims to outperform zlib everywhere, and it usually succeeds. Like I haven't found a case where ZSTD wasn't better than zlib. All of this is, of course, dependent on the data distribution and so forth. But if you are at liberty to change the compression algorithm, it is almost never the optimal choice to use gzip. Then again, gzip is in use everywhere, and there are good reasons for using gzip. For example, your browser can decompress it, and so forth and so forth. So if a change of algorithm itself is not possible, you can still change to a fork of zlib that will be faster. Here's a diagram, by the way, of a whole bunch of compression algorithms plotted with a plot of their compression speed against their compression ratio. And what I talked about with the Pareto frontier is essentially this line here, where for a given speed, you can't find a better compression algorithm on the diagram. And it is worth comparing these things for your data. What I'm showing here are actually performance data that Amazon published comparing their fork of zlib to baseline zlib. And they have a drop-in replacement for zlib called zlib-ng. And we can see here that the orange bars are often twice as high as the blue bars, which are the default zlib. So if you see a heavy use of zlib in your fleet and you're not at liberty to choose a different compression algorithm, do consider faster forks of the same library that are drop-in replacements, because you can get a whole bunch of cycles back for essentially free. Okay, last topic of the day, serialization and deserialization. I mentioned earlier that people often spend an extraordinary amount of time in serialization and deserialization libraries, and that extraordinary amount of time is is often easily recouped, because serialization and deserialization is fundamentally not always very complicated. So one example here is we looked at a very large PySpark job that came from CERN. So CERN published an article about using PySpark for machine learning workloads in high energy physics and a data set associated with it. And then when we looked at where CPU cycles are actually spent when you run that job, it turned out that 20% of the CPU cycles were spent in serializing Java objects to Python, and then another 10% were spent in deserializing those serialized objects back into Python. So that's a whole bunch of compute, like more than a quarter of your compute is just spent in serializing and deserializing data that you want to compute on. Another example that we saw where a customer was running a large machine learning workload again, using MSGPack for serialization and deserialization, which was eating a tremendous amount of CPU cycles in their infrastructure. And they then proceeded to replace MSGPack with a library called OR MSGPack, which was a Rust implemented Python message pack extension. So it's like a Rust library that links nicely into Python that performs the same job as MessagePack. And rolling that out reduced whole cluster CPU load by a whopping 40%. And what I'm trying to emphasize here is that it is very common that if you're using any form of serialization format, that you can find a faster way of serializing and deserializing the same data, and you can get a whole bunch of resources saved by doing so. All right, so the summary of the talk really is, where have all the cycles gone is often a difficult to answer question, and fundamentally a very surprising, well, not a surprising question, but a question with very surprising answers. And once you start doing fleet-wide continuous profiling, you find a surprising number of surprising sinks for CPU cycles, things you never anticipated would have happened. I often liken it to switching on the lights in a basement that nobody's visited for 20 years. You just find a lot of dust and also a whole bunch of bizarre objects you had not anticipated finding. The other thing that's happening is that fleet-wide continuous profiling, after having been available inside Google and Facebook for a while, is finally becoming available to people outside the hyperscalers. And I think it's actually a fairly big trend. I think that by 2026 or 2027, the majority of large infrastructures will be doing some sort of continuous fleet-wide profiling in order to enable developers to continuously refine the efficiency of the entire data pipeline. Okay, so what can people do at home, essentially, to do continuous profiling of their systems? There's a number of different continuous profilers available these days. The first one I'd like to mention is from Pixie Labs. It supports C++, Go, and Rust. It requires symbols for C++ and Rust binaries in production. But it looks very, very sweet. Pyroscope is an open source system-wide profiler. I haven't actually used it myself, but it looks as if it's possible to do whole system profiling. It should require symbols on the machines where you deploy it as well for native code. And then there's Protfiler, which is the continuous profiler my company is building. And we support C, C++, Rust, Go, JVM, Python, PHP, Perl, and the kernel. Clearly, well, I think it's a very nice profiler. All right, and that's already the end of my talk. And I am open to taking questions.